ladies and gentlemen, and thank you, Rob, for that kind introduction. We heard yesterday a lot about the larger systems, waste heat recovery, both steam and ORC, very impressive large systems that we saw. The challenge is that most of these are going on to kilns that are more than 3,000 tonnes per day. The majority of the European market is quite small and really quite well thermally optimised. So what you're left with is waste heat, which is at low grade, typically below 300 degrees C. So the challenge really is trying to find or come up with solutions for these installations where you can hit the sweet spot with the internal rate of return of greater than 14% to give you the paybacks that you need to make these projects go. Because when you think throughout Europe, there's probably only, well, there is 7 plants. It's not very many, and we have to ask ourselves, why is it not really been rolled out yet? A number of reasons, obviously, that we know, but electricity prices dropping back has been a key thing, as well as many changes in the market as well. So the challenge is to find the right projects with the right return on investments, and it fits perfectly. So I'd rather change the title of my presentation really to sizes and everything, and really follows on from what was said earlier on. So it would be nice to change it. I'm going to talk about the risks of installation, the things that we've learned. So Heatcatcher started 5 years ago. We operate out of the Innovation Centre in Sussex University. The first few years we was in the research and development, looking at heat modelling and forecasting. And really the last 3 years we've developed in projects, built a project pipeline over sort of 20 projects across the lime and cement industry, looking at where we can tap into these sources to generate electricity. We've even been paid for about 6 feasibility studies by cement companies, which is quite impressive. So we've managed to complete these and a full specification design on a clinker cooler, as well as building the first plant, which I want to talk about the lessons that we learned from building the first plant. So 2 years ago, I presented this design at CemPower in June 2013. And at that point, I said that this was our basic design that we were going to be installing. And it was really based around a 600 tonne per day kiln at Thristleton Works, which was then owned by Stigley Dolomite, which has now become part of the Waste Group. And the project really was to try to get a payback within 5 years, plus we got some grant assistance as well, about 20% grant assistance, which meant we got down to about a 4-year payback on the project. You can see there, we're not an ORC manufacturer, but we do look at what the best available technologies on the market and promote those to the projects to see which fit the best for the waste heat profiles that we've got. But we are a technology partner with GE Energy. So the ORC you see down the bottom there is 125 kilowatt, do 140 kilowatt module now. And the clever part about this technology is the integrated power module. So it's got a small micro turbine inside, and on the right hand corner there's a small micro turbine there. It's an integrated power module. So within that you've got the alternator as well, and the power electronics feeding it. So it's a sealed unit. So from a refrigerant point of view, you've got less risk of leak, and the run hours on that are 100,000 hours. So you've got a lot of reliability for a long time. And back to there. So we're inside the containers. So just following on from Rob's idea about putting them inside containers, we've got 425 kilowatt ORC generators. We've got the condensers on the top. Our main means of control is the modulating damper. At the moment there's an ESP on the exhaust of the kiln. It's about to be changed to a bag filter. And our main means of control is as we open the damper up, comes across the heat exchanger, heats up just a pressurised hot water loop that then feeds all 4 of those ORCs. And the ORCs will take what energy they can take from that thermal loop. So the control mechanism is key to making sure we're optimising and get as much net electricity out of it as possible. So the system, gross installed, is ½ megawatt, and it cost us £1.3 million to build. So if you use euros, although not very favourable at the moment, you're looking at 3,000 megawatt, 3 million euros per megawatt as an installed cost at the moment for this full installation, full turnkey project. And the operating costs, we've now got a 10-year contract to apply for this. So we're 18 months into it, so we've learned a lot of lessons. about how we would do it again differently, optimise performance, automation, all those things that can help to reduce costs on next projects. The key part as well was making sure that when we designed the heat exchanger that we didn't create too much back pressure on the induced draft fan, because if you create too much pressure there, your fan has to work harder and can negate some of the electrical efficiency benefits that you are producing. So on this plant, we're producing 448 kilowatts net, which is about 25% of the site load. So it's a site load reduction of 25%. This is what it looks like now after we built it. So 6 months after I'd spoken at the presentation, we had the plant in December. We opened up the damper, put some heat onto the heat exchanger, saw the water run up 90 degrees C, and the turbine started to generate electricity. So that was a proud moment for me after many years of getting to that point, and a nerve-wracking one as well. But the system started to generate, and then by February, we fully handed the project over, fully commissioned, ownership passed over to Steely, and now, I mentioned, we've got a 10-year operating maintenance contract, so we look at it, we can see it on our phones, how it's operating, we're constantly looking at it to see how we would change performance and control strategy for the future. You can see there that we've got the condensers sitting on top of each 20-foot container, and this is a direct refrigerant cooling system expansion. So there's only 2 loops. There's the primary loop, pressurised hot water, and then the direct refrigerant loop through the condensers. What we've put on top of these condensers are EC electric commutated fans, very low, very high efficiency. So when we do benefit, and this is in the north of England, so it's even cooler than here, so when we do benefit from low ambient temperatures, those fan powers are absolutely very small, very minimal. So we get really high efficiencies from the plant. Parasitic losses are very small on the plant from that benefit. The condensers are probably 20% oversized, but it does allow us to get more efficiency, but we probably wouldn't design them as large next time. So there's a cost saving there. So there's lots of lessons to be learned for cost savings to get these this installed cost per megawatt down in the future. You can see that we've got the heat exchangers across here. We have opening hatches, and a hydraulic self-cleaning system is what we designed to be used. The dust isn't large, it comes out from after the ESP, after the filter, so the dust levels are quite low. But the one remaining issue that we've got with the plant is on controlling the dust levels. I'll mention that in a minute. So integration challenges when we're looking at the plant, they're pretty similar for every plant. Where you're going to locate your heat exchanger, and there are 3 or 4, maybe 5 positions within a kiln that you can tap into to pick up the heat. We heard earlier on about the preheater and the air quench cooler, but there's also opportunities after the filters as well. We've got to make sure that our back pressure is as low as possible, so we don't want our ID fans to work harder than they need to. We need to be thinking about dew point. So on the kiln side, we have to stay above the dew point, make sure we don't get corrosion in the ductwork and the tubes as well. On the cooler side of it, it's not so important because the air is much drier and you've got less moisture in there, so you can drop the temperature lower. Then we're thinking about the erosion, so the type of dust. What we do is we put in a test tube in a position where we're looking to tap into the heat exchanger. We install a test tube, leave it in there for 3 months, take it out, see what condition, whether we've got erosion, corrosion, what type of, how sticky the dust is, understand the characteristics. Take the dust away and actually analyse it as well. Because we're based at Sussex University, we've got the laboratories to actually understand the dust itself when designing the heat exchangers and the cleaning systems. So with the cleaning systems, you've got a number of options. You see, you've got a cyclone to take out some of the dust previous, you've got hammering, which you see. We've got the sonic horn that we were talking about yesterday, and Donald gave a presentation on that, so we'll talk about how we're going to introduce that. And then hydraulic brushing system. That's the key issue is always about the heat exchanger itself and how you're going to integrate it. And then what's going to do to the induced draft fan? Is it going to increase the pressure? Is it going to increase the fan power in the case of on the kiln side? Or is it going to reduce the fan power when you're looking at the cooler side? I'll explain how that happens. You're going to have an effect on the stack buoyancy because you're changing the temperature. And because you're changing the temperature, the actual fan needs less power, but you've got the resistance to overcome. You've got the environmental permit, the variation. This is something that's coming up more because of the tighter restrictions on the emissions, industrial emissions directive, which came into play this year, you know, these consideration of when you're putting a heat exchanger, what's it going to do? Well, how's it going to change the flue gas characteristics? So there's a certain concern or a clearer, some consolation that you need to give really when you are looking at these changing potential emissions. So I mentioned earlier about the issues that we've got with the dust. The ESP is on its way out, so we've got higher dust loads than we would be seeing at the moment. But even so, we designed the system to have a hydraulic cleaning system. And between each one of the tubes is a stainless steel brush, and it would move backwards and forwards continuously on a hydraulic rack. When we installed it, as the corrosion built up, even on the stainless steel brushes, it started to jam. And those stainless steel brushes got to a point where the hydraulic ram wasn't strong enough to push the heat exchanger cleaning system along. Hence, we fitted a sonic horn, and we've installed this, tested it. The key thing that we had to do to start with was to make sure that we weren't disturbing the noise from the surrounding area. So this was just a trial hall that we put in to make sure that the emissions or the local noise levels were within limitations, because there's some neighbours that aren't happy about extra noise. So we had to satisfy that. But there's no acoustic attenuation on that, which could be added at a later stage. So for learning from lessons from this, we're now installing 2 of Donald's sonic horns in positions that are well sitting on top of the heat exchanger to push the dust through. And we shall be monitoring that and learning a lot about how it operates, because it's important for future projects. The cost of the sonic horn, as you can imagine, is a much cheaper option than a hydraulic ram with all those stainless steel brushes in. That's another cost saving. So our installation is at the tail end. After the bag filter, we've got 245 degrees C, and we've got low dust loadings, less than 20 grams, but we've got low power and no generation because the temperatures drop down at this point. Obviously, we saw the preheat side, where most of these installations are capturing the largest amount of energy. But the issue we've got with this, I mentioned about emissions, is that if you're bypassing your gas conditioning tower, is there going to be issues to the changes in the flue gas characteristics because you're not cooling it as quickly? This is something, the problem's got to be solved, and people have got to understand that they're safe with their plants because they're burning a lot more alternative fuels. They're not going to get issues with emissions. So from the kiln integration side, if you're looking at the preheat boiler, ACK mentioned yesterday that many of the projects are horizontal cross-flow on the preheat boiler side, and they're designed for low back pressures. The dust at that point is obviously very sticky and very fine and very high loading. So hammering system is the most commonly used technology to remove the dust at this point. On the filter, on the ID fan performance, then this pressure drop obviously has to be kept to a minimum. If we're looking at the tail end, it's much more simpler. You just have a vertical cross flow with a cleaning system as we've designed here. You need to think about what's going to happen to the fan as well. So this is a case study courtesy of Bowden. They kindly let me go to the Holcim plant in Romania, set it up for me to go and have a look at their installation there. It was very impressive. Sabrina mentioned yesterday, this is the one in Romania. It's a 4 megawatt system, 2 horizontal cross-flow boilers, and the hammering system. I did have a video of how it works, and it was there, but I didn't want to risk putting it on with to transmit it through the internet. It's a continuous hammering system which is working really well. So, summarising on the kiln side of it, you've got a dust that's very fine, very soft and sticky. We always require 100% isolation from the process itself to make sure that we're not going to interrupt the process if there's any shutdown required of the ORC. The boiler has to be designed for minimal pressure drop. We've got much higher dust loads there, typically over 100 grams per normalised metres cubed. And the hammering system is the most commonly used system. but we need to think about the change in emissions if we're going to slow the cooling system down rather than using a quench tower. On the tail end, we've got lower dust loadings, less than 20. Typically, the legislation now is less than 10, and so many people are having to upgrade their bag filters, ESPs to bag filters to get down to this limit over the next few years. And we've got a reduced temperature at the ID at the fan, so we have to work out what the change in fan power is going to be at that point, using fan curves. Is it in a better position on the optimised position on the curve? So then going to the air quench cooler, which is where most of the interest has been. Many of the companies are more comfortable with making you look at the quench cooler to start with, mainly because the dust is much drier. There's less effect on the emissions. You've got two positions that you can collect it from, and one position here which is straight after the cooler and prior to any cooling system. So often you would have cooling fans, or you could have forced air being injected in to cool the air before it goes to the bag filter. So you'd be seeing 320 degrees C here, maybe dropping it down to 150, 160 before it goes to the bag. So there's a lot of energy lost as it goes into this system with cooling. Placing the heat exchanger to do the work of the cooling fan or take away the induced draft that's going in to cool it can save a lot of power from the fans or from the ID fans. And this typically, we're finding there's an extra 10% of electrical efficiency or savings from the cooling fans, and maybe up to 30% when you are pushing in force air. It's going through your bags and through your fans. So there's lots of additional savings from the fan side of it that can improve the payback and return on investment for the projects on the cooler side. So there's less reason really to put it after the bag filter, unless you've still got a relatively high temperature there. Obviously, this dust here is extremely abrasive and high chunks and high loads, so you have to be putting in a deduster previous to the heat exchanger to take that out. So putting it after that means the cost saving for the deduster, but you've got a lower energy availability. So all these things need to be cost analysed to work out the best positions, the best combination to give you the project with the best internal rate of return. So on the cooler side, typically the vertical cross flow going down, but you'd have a deduster previous to that heat exchanger, and even go to a fin tube to improve the efficiency if you've taken enough of the particles out of the dry dust before the heat exchanger. What's important if you're putting this before the bag filters is your control strategy is really to protect the bags, because you don't want the high temperature going onto the bags. So your main reason, your main control is you still need your backup cooling system, and you'll be controlling between the two to make sure you've got that to protect the bags in the event of the G59 when the ORC needs to be out because of electrical and there's still some thermal inertia in the systems. There's a lot of thermal inertia in these plants. It takes about 20 minutes, half an hour to get them up to full speed, and hence it takes 20 minutes, half an hour for them to ramp down as well. So there's a lot of thermal inertia in these plants, and which means obviously from an electrical point of view, you have to be able to isolate them immediately. G59 regulations, also where's the energy going to go once you stop the plant? You have to design to make sure you've got that. So this is a design that we've completed for an air quench cooler. The simple control mechanism is an actuating, modulating damper here. So the air comes off the cooler at 300, goes into the air heat exchanger traditionally, and then to the bags. So this is the way it means cooling it prior to going to the bags and reducing the temperature. What we're going to be doing is modulating it, taking it through a deduster. The trick with a deduster is to take out as much of the high level particles as possible, and the way you design that, using computational fluid dynamics to ensure that we've got that to an absolute minimum, and the deduster, so the percentage of that being taken out, and what's left will obviously go to the heat exchanger. So the sonic horn, design of the sonic horn, how much percentage can you remove of the sonic horn gives you what you've got left on your heat exchanger. So when you design your heat exchanger, let's say you've got 20% dust left on there, then you need to over-design your heat exchanger, which obviously is capital costs. So over-designing, physical size. So the more we can take out, the less over-designing we need to do here, the more reduction in capital costs. So summarising on the cooler side of it, we've got very dry, abrasive dust. Once again, we need to isolate it completely from the system. We would need a deduster or a cyclone prior to the heat exchanger on that side of it, if it was before the bag filter. The CFD analysis is there to minimise the pressure drop. It's important that we keep this pressure drop to an absolute minimum, not just for the heat exchanger itself, but also for all the ductwork, the integration, all the dampers, everything needs to be kept to a minimum because that's an energy loss. So before the installation, we've got high dust loadings there, and after the filter, we've got lower dust loadings, so we wouldn't need the deduster before, after the installation, but we'd still need a cleaning system. So really, just to summarise, we're not an RC manufacturer, but we do try to find the best solution for the waste heat profile that we've got. So really the key for us as a developer is to make sure that we keep reducing the costs of installation below 3 megawatts per 3 million euros per megawatt. To push these down to 3-year paybacks is a real way this technology is going to get rolled out. Because if you get below 3, then you can either be a capital decision from the company or any third-party financer would love to fund a project that's got a 3-year payback. So the important thing is that what we can deliver really is to make sure that we design this, we optimise it, we look at all the options, we're making sure that we've got the best solution that we can provide that's on the market and the lowest operational risks. And it's not always about efficiency of the ORC, it's about the capital cost versus the net output to make sure that we get within these rates of returns, because they're the things that are going to get the project signed off. You can have a really high efficiency project, but it can sit there forever if it doesn't meet those capital constraints, which is obviously the key to everything, unfortunately. It's a shame when you're technical and you love to make sure that you've got the most efficient, but it's the finance guy that signs these projects off. So really, our goal is to try to meet that criteria as well as provide a system that's got the lowest operational cost and risk. Okay, thank you.